Welcome to the third video on our journey through the P-block elements and their compounds. And in this one, we'll be taking a look at the at group 14 and the elements and compounds that are formed there. Now I've got group 14 highlighted at the top here. It's called the carbon family. It contains carbon, silicon, germanium, tin and lead. And yeah, also contains a bit of everything structures wise. So carbon's a non-metal, silicon and germanium are metalloids or semi-metals, and tin and lead are metals. They've all got 4 valence electrons, but they're physically and chemically very different from each other. And the oxidation states here vary from +4 to -4. And it's really silicon you'll find the most variation. But +4 is more important at the top of the periodic table. And then as we go down the group, +2 becomes more important. And this is again due to the inert pair effect. So much like the last lecture, we're going to focus mainly on the top 2 elements of group 14. They do more chemistry, more exciting chemistry. And going down the group, looking at things like lead, you just have to know that it's dominated by the inert pair effect. So the +2 oxidation state is more important than the +4. But yeah, really there isn't so much chemistry going on down there as there is at the top. So we'll start by looking at carbon. It's one of the first elements known to humans. It was diamonds are discussed in the Bible and even older Hindu manuscripts. It's key to all known life. So yeah, we are built up a lot of carbon, so DNA, proteins, hydrocarbons. Yeah, most living things are mainly carbon. For example, a 70-kilo human is 16 kilos of carbon. And carbon in the natural world has the very unique ability of what's called catenation. So it forms covalent bonds with itself to give chains and rings. And there are more than 10 million compounds of carbon known. There are also quite a few allotropes. So there's 3 common types of crystalline ones, and we looked at these in the solid state, solid structures lecture as the example of allotropy. So we've got graphite, diamonds, and fullerenes, which are the balls. And there are also a few amorphous allotropes like charcoal and carbon black. So yeah, essentially what you get when you burn things. So looking at the oxides of carbon, there are actually quite a few, but there are 2 that are super common with, I imagine you're quite aware of already. So these are CO, carbon monoxide, and CO2, carbon dioxide. And these are from the combustion of carbon or anything organics, anything carbon containing. Which is formed is usually mainly dependent actually on how much air is present, how much oxygen there is to react with it. So when the air supply is limited, you get more carbon monoxide, and this is toxic. So in your blood, we've got your blood, our blood, everyone's blood. There's hemoglobin, which is an ion complex, and this is what takes oxygen around the body. So oxygen will coordinate to this ion in the hemoglobin, go around and be released where oxygen is needed. But CO can irreversibly bond to the ion in the hemoglobin, and then when CO is irreversibly bonded, oxygen can't be, and then we run out of oxygen. The other ones I was talking about, so there's carbon suboxide here, C3O2, and also a very larger carbon oxide structure here. These are much less common. I think unless you work in the research field specifically looking at these, you'll never come across these. But they're much less stable. C3O2 readily polymerizes. And then coming to CO2, this is the one we hear the most about. So it's the culprit for global warming and climate change. We've released loads of it since the Industrial Revolution in 1750. So since we worked out that we could burn fossil fuels and burn most things to make power and transport, the atmospheric concentration has gone up from 280 ppm to 412 in 2019. And I've got an example on the next slide showing this. So you can see during the year it actually fluctuates a bit. So in the summer months it goes down, probably because we're not using so much heating. But year on year you can see it's absolutely flown up. Even from the 60s it's gone up at 100. 100 ppm. And if you want to see what it is now, which I think it's closer to 430 now, so even in the last 2 years it's gone up 20 ppm. This is where I got all these this data from. And yeah, if you're interested in how greenhouse gases work, which I'm not going to ask in the course, but yeah, if you want to know why CO2 increases the global temperature, there's a nice link down here that I will put in the description of the YouTube video as well. So moving on to the halides of carbon. These are all covalent molecules with tetrahedral geometries. So the carbon orbitals are sp3 hybridized. And under standard conditions, the fluoride, the CF4, is a gas, CCl4, which is chloroform, is a liquid, and the bromide and iodide are solids. Now, the stability decreases as the halogen size increases, and this is because bond enthalpy decreases due to a reduction in orbital overlap. So yeah, we've seen it quite a few times during the course. If you're looking at something small like carbon bonding with something big like iodine, there's just not much overlap in the bonding orbitals. So yeah, it's not so strong. CF4 and CCl4 are very unreactive, but the bromide and iodide are prone to combustion. So yeah, you can light them. So moving down group 14, we come to silicon, which is the second most abundant element in the Earth's crust after oxygen, which is actually what is usually bonded to how it's usually found. So this is silicon dioxide. It's got a crystalline form called quartz and a non-crystalline form called flint. It's also found in a lot of rocks and minerals, things like that. Like sand on the beach is usually a lot of silicon dioxide. But then, yeah, it gets turned into other things. And there's quite a few uses for it. So it's used a lot in the manufacture of semiconductors. So yeah, silicon itself is a semiconductor. And it's also used to manufacture plastic-like materials called silicones. It could have chosen a name that's slightly more different than silicon itself. But yeah, so these silicones are polymer plastic-like materials, as I say. Now with a low molecular weight, that's what this MW is, so shorter polymers of silicone are used as lubricants, things like WD-40, whereas high molecular weight silicones are used for spaceship parts, super bouncy balls, bathroom sealants, and these sort of silicone molds you get for the kitchen, like loaf tins, all of that. And then you've also got medium molecular weight silicones, which are used in fabric softeners, hairsprays and hand creams. Hair conditioner especially, if you have a look on the back of the a hair conditioner bottle, they usually contain a lot of silicones. So let's look at the oxides of silicon and how they compare to the oxides of carbon we've already talked about. So silicon, as we said, is present as silicon dioxide, SiO2, and this forms covalent network structures as opposed to carbon dioxide, which is just a discrete molecule with multiple bonds. And we can see by looking at the enthalpy change when going from a network with single bonds to discrete molecules with double bonds, that in the case of carbon, it's favourable, it's got a negative enthalpy change, whereas for silicon, it's unfavourable, it's got a really large positive enthalpy change. And this is to do with the relative bond strength of a CO double bond compared to a SiO double bond, and also the strength of the silicon oxygen single bond compared to the carbon oxygen single bond. So in the case of the carbon oxygen double bond, this is stronger than the silicon oxygen double bond because of the distance sensitivity of pi bonding. So remember, a double bond or pi bond is, let's take we'll call it X double bond O. So they've got a sigma bond, sort of a single bond, from, in this case, what's going to be sp2 hybridized orbitals overlapping across the middle here. Well, actually, on the oxygen, it's probably just a normal p orbital. So it's got the sigma bond here, which happens very easily, and then the pi bond contribution is from these p orbitals that overlap side on and give electron density above and below the sigma bond. Now it's this pi bond that's incredibly distance sensitive because they need to overlap side on. And since silicon's much larger, it doesn't overlap with the p orbital of the oxygen so well. So the pi bond is weaker. So that's why the CO double bond has a much higher strength than the silicon oxygen double bond. Now conversely, the silicon oxygen single bond is much stronger than a carbon oxygen single bond. And this is because we've gone down the group. Silicon has a lower electronegativity, and that's what's shown in the bottom right here, the electronegativity. You can see there's a bigger difference between silicon and oxygen than carbon and oxygen, and this makes the bond more ionic, and ionic bonds are stronger than covalent bond. So because of this difference in what's stronger between a double bond and a single bond, the network with single bonds is more favourable for silicon, and the discrete molecules with double bonds is more stable for carbon. So moving on to the halides of silicon, these are fairly similar to the halides of carbon. They're tetrahedral, and at room temperature the fluoride is a gas, the chloride and the bromide are liquids, and the iodide is a solid. So a slight difference here. With carbon, the bromide was a solid also, here it's a liquid. But like carbon, they all have a tetrahedral structure. But unlike carbon, they react with water quite readily. Like if you have a silicon chloride, is one that I've used quite a lot in the lab, or should I say can't use too much in the lab. It's incredibly reactive towards water in what's called a hydrolysis reaction. So the water will break the silicon chlorine bonds and form the oxide, silicon dioxide and hydrochloric acid. So if you've got a bottle of silicon tetrachloride, you should really keep it in a desiccator and make sure there's no water, because once you open it and water from the air gets in, slowly starts hydrolyzing it, and then you no longer have your chloride, you just end up with a bottle of silica. Why is this? It's because the carbon is smaller. So if you see the carbon surrounded by these halides, it's protected. We call it sterically shielded. So the halides around it are big enough that the water can't actually get to the carbon. Whereas in the case of silicon, silicon's a much bigger atom. The halides don't really cover it. So the water can attack the silicon. And finally, let's have a quick look. One further down again, germanium. I've put this in because I find it a really interesting example of how the periodic table both works and has worked. So when Mendeleev first made it, nearly 100, well, just over 150 years ago now, germanium wasn't discovered. However, he put it in, he called it ecosilicon, and just guessed at what its properties would be based on the elements around it. And you can see he's got his predictions under ecosilicon and real germanium, and they're incredibly close. He's done a very good job. So that's how just an example of how the periodic table, even before we knew what some of the elements were, was made in such a way that you can predict what elements should be there, and indeed it worked.